All right, so for the part B here, we'll look at examples 2 and 3. So this is understanding what's called end behavior of polynomial functions. So the question is, how do the sign of the leading coefficient and the degree of the polynomial affect the end behavior of the graph of the polynomial function? So what this is saying is by looking at that lead term, so you look at both the coefficient and the degree of that lead term, it tells you what this function is going to do at the ends. And actually, this ties directly to what we did back on that first example. Let's talk about it real briefly. But we learned on any of these odd powered functions, they had this kind of shape to it. And any of these even ones had this kind of up and up type thing going on. So this actually is going to carry over here, and we're going to use that concept with these. So there's 4 different scenarios here. So if you look at all 4 of these boxes that you got on your notes, you have odd degree, positive leading coefficient, you have even degree, positive leading coefficient, and then the other opposites would be odd degree with a negative coefficient and even degree with a negative coefficient. So let's just start with the first case scenario here. So here's a bunch of different graphs that all have odd degrees and positive leading coefficients. So, there's like a y equals x, and there's a 0.5x to the third, and there's a 2x to the fifth. Sorry, they're real faded, but either way, in every one of these where you have an odd degree and the leading coefficient is positive, every one of these starts down here and ends up here. And so what we can say here is we're going to describe this, what we call end behavior, as saying what happens as x goes to positive and negative infinity. So the way we're going to word these is, in this case, this is for any time you have odd degree with positive leading coefficient, we would say, let's see, where's the best spot to write this? Probably here. We'd say as x goes to negative infinity, so as we're going to negative infinity on our x, our y's are also going to negative infinity. And in the same case, as x is going towards positive infinity, so as we're going out this way, the y's are also going to positive infinity. So that's how you're going to see it mainly in like the assignment and stuff like that. Some texts, and when I learned this, it was also referred to as what we call a down and up end behavior. So you can use both phrasings there, but these are both kind of the ways we talk about this. In other words, it starts down and it finishes up. So before we hop across, let's hop down at the other odd function here. So if your degree is odd, but your leading coefficient is negative, that inverts the graph. So now they're going to start up here, but they're going to finish down here. So all it really does is everything's opposite. So notice these are still first power and third power and fifth power, but now all these leading coefficients are negative. If you can't see them, they are, trust me. So in these cases, it's just kind of the opposite. Here, as x goes to negative infinity, y goes to positive infinity. Because now, as you're going in this direction, the y values are going up. And as x goes to positive infinity, so as you work to the right there, your y's all go down. So they go to negative infinity. So it's just the opposite of what we saw on the other one. This one, in other words, we would call an up and down graph, because it starts up and finishes down. Those are other ways to describe that end behavior. For the even degrees, these will always be doing the same thing. They'd be both going up or both going down. So to word it in the same sort of way, if we want to say as x goes to negative infinity, so as we go to negative infinity, anything with a positive lead coefficient, think of how x squared works, is going to be going up to infinity. And as x goes to positive infinity, so as we go this way, the graph still goes up. So in this case, you notice you get the same behavior out of the y's, where it was opposite with your odd degrees. This one we would refer to, as you can imagine, an up and up function. And then lastly, the last combination is when you have an even degree, but a negative value in front of this. We saw a lot of this with x squared, so this is like a negative x squared type graph. And so in this case, we'd say as our x goes to negative infinity, negative infinity, our y also goes to negative infinity. And as our x goes to positive infinity, our y still goes to negative infinity. So the takeaway from this, again, should be that based off just that leading term, you can look at the sign of the coefficient if it's positive or negative, and you can look at the degree if it's even or odd to know what the graph's going to basically look like. And this one you could also call a down and down. So let's see if we can do this with some kind of just generic problems. So if we jump down here to these triads. So here it says, okay, here's some big old crazy looking function, but it says use the lead coefficient and the degree to determine the end behavior. Okay, so we don't care about any of this mess. All these terms after lead coefficient don't do anything for the end behavior. It's just the lead term, which is a 2x to the sixth. So it's positive and it's even. Okay, positive coefficient, even. So once you learn the rules, you're going to be able to just answer this right away. But if we go look, positive leading coefficient, even degree, positive leading coefficient, even degree, is going to behave like an x squared. It's going to be an up and up. So we can say in this case, like I said, we can describe it as up and up, but you're going to see it in the assignment today basically saying it's like, hey, as x goes to negative infinity, y goes to positive infinity, and as x goes to positive infinity, y still goes to positive infinity. So that's how you're going to want to answer those, or how you're going to be looking at those types of things. The way I remember it, which I think works really well, is I just think of all even powers behave like your x squared graphs. You know those from last chapter. You know, if it's positive, the graph opens up, and if it's negative, the graph opens down. And then all odd powers behave just like linear functions. If they're positive, they go up, and if they're negative, they go down. So in this case, this is a negative odd function. So negative leading coefficient, odd degree, is going to do this. It's going to start up and go down. So in this case, we'd say as x goes to negative infinity, y is going to go to positive infinity. And as x goes to positive infinity, y is going to go to negative infinity. Always going to follow those types of rules. So that's using the lead term to talk about the end behavior. What's the overall graph going to do? All right, so I should be good with that. And example 3 talks about making graphs here. So it says, consider this function. How can you use a table of values to identify key features and sketch a graph of the function? So there's some key things we want to know from this. For one, we know end behavior right away. We can look right at this and we know end behavior. And this is where I like to use the phrase like up and up and down and up and that type of stuff. Is it's a negative odd. So it's going to behave like a negative x squared. So it's going to be a down and down graph. I like to know that right away going into it. I think that's really easy. Also, if you remember from quadratics, the same rule holds. The constant is always your y-intercept. So this graph is going to cross the y-axis at 2. So I can actually mark that right away. So as I'm talking about what this graph's going to look like and so on, I know this graph's going to cross the y-axis at 2. So that same fact that held with quadratics still holds true here. Okay, so other stuff that I don't really know here is some like other values. I don't know what else is going on. I basically know the following things. I know my y-intercept, and I know that in the end it's heading down, and at the start and at the end it's heading down. So this is kind of what I've got. I don't really know what happens in between here. I don't know if there's like some waves to it. I don't know quite what's going on. So at this point, like it says here, it says, how can you use a table of values to identify key features and sketch a graph of the function? So what you're going to find really useful here is some sort of graphing utility, whether it's the Desmos app or your graphing calculator, is you're going to be able to enter it in, and you're going to see what kind of hills and valleys and stuff does this graph have. So I'm going to use the graphing calculator. This is one of these things that I'm going to be honest, I think is really easy on Desmos, but I like to show you it on the graphing calculator because this is what you can use on like the SAT and stuff like that. So if I type in the equation like it is, like so, I'm going to just press graph. And first off, it should do the things that we just talked about. It should be down and down, and it should be crossing at 2, which it is. But now we can also see it has a couple hills and valleys here. In this case, we have some key points. We want to know what these coordinates are. So we're going to figure these out. Now on Desmos, I believe you can just click and it'll just tell you those coordinates. On here, we got to use like our max and min features. But we're going to use those points to basically finish out our graph. So I want to know that coordinate, and that coordinate. And we'll talk about what those are called. So these are what we'd call maximums. And this is going to be a minimum because it's like a low point. So in our trace menu, second trace, we can do maximums and minimums. So if we're using the calculator for this, we go like to, let's say we do the minimum first. We already know that one. That was silly for me to bring up, but that's the one that we already knew it was at 0, 2. So I'm not going to bother with that one. We need the maximums. Sorry. So my maximums, I got 2 of them, and they're going to be symmetric. So really, if I find one, I do know the other. This is where you got to do like the left bound. You press enter. You move to the right. So you got to go past that maximum. Press enter. And then for guess, you press enter near where it's at. And then it's going to tell you, hey, there is this coordinate. And these usually are at pretty weird spots. So I'm going to write this down, and then I'm going to plot it. So again, the coordinate that I got was negative 1.73, comma 6.5. Now, I know this graph's symmetric. You might too. But this one over here is just going to be at 1.73. I can show you real quick if you don't believe me. But if we go through and we do it, same thing over here. We go left bound, click to the right, enter, and 1.73, 6.5. So same coordinate, just on the other side. So those are my 2, what I'm going to call relative maximums. So these 2 values we call relative maximums. And then we already know that y-intercept was a relative minimum. So if you remember that coordinate 0, 2 was a relative minimum. It's the lowest point that graph reaches in that area anyway. So if I plot these points, that's going to give me this wavy shape, and I'll be able to basically finish out this graph. These are kind of what I call my critical points, my key points. So again, negative 1.73 and 6.5 is going to be here-ish. And then the same point on the other side be right here-ish. And now I can draw what's going on here. I can draw this graph going to these points like so. And there we go. So that's my key. I got my 2 relative maximums, my 1 relative minimum. It allows me to kind of see these critical points of this graph. The last little follow-up question here, and this just goes back to stuff way back from chapter 1. It says, how do you use the graph to estimate the average rate of change over this interval? So we did this stuff a long time ago. This is like from the interval from -2 to 0. So at -2, whatever value this is, to at 0, which we know that value is at 2, what's that rate of change? So since I've already got it in here, let's look at what that value was at -2. So at -2, it's at 6. So this coordinate here is this spot right at 6. So from this spot to that spot, we just want to count the rate of change. So it's going to go down 1, 2, 3, 4, and right 1, 2. So down 4, right 2, for a rate of change of -2. That's really just a review concept. Nothing too crazy or too new there at all. All right, let's go with that. Let's see what you can do from there. Have you practice some of these assignments, and we'll finish up this notes and stuff on our next day.